Students, in this class, let us derive an expression for numerical aperture of the optical fiber. So, in order to derive the expression, let us consider an optical fiber with core of refractive index n1, and cladding of refractive index n2 such that n1 is greater than n2. So, this is the optical fiber. The central part is core and the outer thin part is cladding. Okay, core is denser than the cladding, that is n1 is greater than n2. Let the fiber be placed in a medium of refractive index n0. That outside medium is n0. Okay, let a ray be incident at an angle at the entrance of the fiber theta naught. Okay, let a ray be incident at an angle theta naught. Yeah, that I haven't written here. Okay, you have to consider that as theta naught, and theta 1 be the angle of refraction. Okay, so this is theta naught and this is theta 1. If the angle of incidence at the entrance is less than this, okay, so this theta naught forms the acceptance angle, because here I told you, so when this is theta 1, this becomes 90 minus theta 1, and the angle of refraction in the rarer medium, that is in the cladding, when it enters from core to cladding. So here we are getting the angle of refraction as 90 degree. Okay, so then this angle at the entrance becomes angle of acceptance. Okay, so this theta naught is the angle of acceptance. Now, so if the angle is less than this angle, what happens? We have already studied in the definition of acceptance angle. So theta naught is the maximum angle below which, if the angle becomes less than this theta naught, here the angle becomes greater than the critical angle, and we will get the total internal reflection. Okay, so entrance is less than the acceptance angle theta naught. The ray is transmitted through the fiber due to total internal reflection. Okay, now applying Snell's law at the point of incidence O here. At the point of incidence O, let us apply the Snell's law. What is Snell's law? Sin theta naught divided by sin theta 1 is equal to n1 divided by n0. Yes, no? Sin theta naught divided by sin theta 1 is equal to n1 divided by n0. So that implies, so sin theta naught by cross multiplying we get n1 by n0 into sin theta 1 by cross multiplying. Okay. Now what is sin theta 1 in terms of cos? So you can write sin theta 1 as root of 1 minus cos square theta 1. So let us name this as first equation. Now you apply the Snell's law at the point B. Okay, applying Snell's law at point B, we get sin 90 minus theta 1. So this is the angle of incidence here, sin 90 minus theta 1 divided by sin 90. Okay, so what is the refractive index of cladding? That is n2, and this is n1 core. So you can write n2 by n1. So by cross multiplication, n1 cos theta 1 is equal to n2 sin 90, and you know that sin 90 is 1. So we get n1 cos theta 1 is equal to n2, and we got the value for cos theta 1 as n2 by n1. So let us name this as second equation, and from this we can substitute for cos theta 1 here in the equation 1. Okay, so substituting, so we get sin theta naught is equal to n1 by n0. So that is n1 by n0 root of 1 minus n2 by n1 whole square, because it is cos square theta 1. So n2 by n1 whole square. So by taking LCM, we get n1 by n0 into root of n1 square minus n2 square by n1 square is equal to n1 by n0. So in the denominator, uh, so this is root of n1 square, so that will become n1. Yes, no? So you can remove that square root in the denominator, so that is n1. So n1 n1 cancels, so we will get sine theta naught is equal to n1 root of n1 square minus n2 square, this n naught. So what is this n naught? N naught is the refractive index of outside space where this optical fiber is kept. So let us consider this as air or vacuum, for which n naught is the refractive index is 1. So n naught is equal to 1, we can substitute. So sine theta naught is equal to root n1 square minus n2 square. And what is this theta naught? This is the angle of acceptance. Okay, so that can be defined as sine inverse of this. So, and this sine theta naught is also known as numerical aperture. What is this numerical aperture? It is the of the optical fiber is the light collecting ability. That means as this value increases, root of n1 square minus n2 square increases, the ability of collecting light of the fiber also will be increased. Okay, so that is known as numerical aperture, and this is only a numerical value because n1 and n2 don't have any units, so we can get numerical aperture as only a number. Okay, so is the light collecting ability of the fiber and is defined as the sine of the angle of acceptance, sine theta naught. If any of a given fiber is more, then more light is transmitted through the fiber. Okay, this is the derivation for numerical aperture. And next is, what is the meaning of fractional refractive index change? That is represented by delta. Okay, the ratio of difference between the refractive indices of the core and cladding to the refractive index to the, so I would have written here, okay, to the refractive index of the core. Okay, so that is equal to n1 minus n2 divided by n1. So just you do the correction here, it is not index change. So the ratio of difference between the refractive indices of the core and cladding to the refractive index of the core is known as the fractional refractive index change. Okay, just it is missed here, so you just make the correction. Next, if n1 and n2 are the refractive indices of the core and cladding of the optical fiber respectively, then fractional refractive index change delta is equal to n1 minus n2 divided by n1. As n1 is always greater than n2, delta is always positive because this n1 minus n2 will be positive, so the ratio will be positive. For effective transport of light through the fiber, delta is very less than 1. Okay. Now, typically delta is of the order of 0.01. You see, it's very less. So, we have Na. Okay. We can have an expression Na in terms of delta. Okay. So, that is what is Na? Numerical aperture, and that is sine theta naught. Okay. So that is root of n1 square minus n2 square. So it is, you know that the formula a square minus b square can be written as a minus b into a plus b. So that is written as a plus b into a minus b, both are same. So n1 plus n2 into n1 minus n2. So now you multiply and divide by 2n1. So the value will not change. So this n1 plus n2 divided by 2 you can consider, and n1 minus n2 divided by n1 you can consider. So this is the average value. Actually there won't be much difference between n1 and n2. Obviously n2 is less than n1, but it is little less than n1. That means the difference between n1 and n2 is very less. Hence n1, we can consider n1 nearly equal to n2 and n1 plus n2 as the average value. Okay, so that is equal to n1. Okay, so nearly equal to n1. So we can substitute for n1 plus n2 as n1 plus n2 divided by 2 as n1. Okay, and you know that n1 minus n2 by n1, what is this n1 minus n2 by n1? The ratio between the difference of the refractive index of core and refractive index of cladding, and the refractive index of the core. So this is known as uh, fractional refractive index change. So that is represented by delta. Okay, so here, so that becomes root of n1 into delta into 2n1. Okay, so you know that n1 square, so root of n1 square, you can take n1 outside, so root of 2 delta. So na is directly proportional to square root of fractional refractive index change. Yes, no? So this equation implies that Na is dependent only on the refractive indices. Yes, no? What is Na? Na is root of n1 square minus n2 square. It depends only on the refractive indices. Or it is given by n1 into root of 2 delta. Delta is n1 minus n2 by n1. So all are refractive indices only. So that's what Na is dependent only on refractive indices of the core and cladding materials, but not on the size of the optical fiber. It will not depend on the size. Okay, it depends only on the refractive indices of the optical fibers. So the typical value of Na for fibers ranges from 0.1 through 132 to 0.5. So numerical aperture is directly proportional to the square root of the fractional refractive index change. That's what here Na is equal to n1 into root 2 delta. Now let us consider the problems from on numerical aperture and this fractional refractive index change from 2019. You see here what is asked. An optical fiber has numerical aperture 0.32, it is given, and refractive index of cladding is given. Calculate the refractive index of the core, acceptance angle, and of the fiber, and the fractional refractive index change. Okay, so what is the solution? First you have to write all the given values, and what is to be calculated you have to write. N1 is what, theta or naught is what, and what is fractional refractive index change. So you should write all the expressions. So you know that. So substitute the value of n2, so square on both sides. So the square root is removed. So n1 can be calculated like this. So we get n1 is equal to 1.51, which is greater than n2. Okay, and acceptance angle is just because Na is given. So sin theta naught is Na. So if you take the inverse of that, that gives you theta naught. That is acceptance angle. So theta naught we get 18.66 degree. In that I would have written here degree. So always you should write the unit. Okay, so what is delta? Delta is n1 minus n2 by n1. So this is only a number. So delta is equal to 0.02. Okay, one more problem from 2020. So here, calculate the fractional refractive index and numerical aperture of an optical fiber made of core and cladding of refractive indices 1.504 and 1.469 respectively. So this is actually the last year's question paper, September. So the exam took place in September. So that is for repeaters. So because the freshers didn't have any examination. So this is refractive indexes of core cladding are given. So you can directly find out Na and delta. You see delta I have found here. Okay, just substitute and you got delta is equal to this much, and numerical aperture this formula. So we can, you need not do the square of n1 square and n2 square. So we can do like that, like this also. So finally we get NE is equal to 0.3225 or 0.323 also you can write, or 0.32 also you can write. So this is the value of numerical aperture. So this is the end of the class. Thank you.